Hello, thank you for coming to another lecture for Introduction to Computer Graphics. I'm gonna just dive in and start talking about today's topic that is going to be triangular meshes, right? So last time we talked about surfaces in computer graphics, and today we're going to zero in on triangular meshes. And there's a reason for that. Now, we talked about different types of surface representations. And at the end, I said that probably the most popular way of generating 3D models today is using polygonal meshes. And in the polygonal meshes, what people typically prefer are quad-dominant meshes. These are meshes that are mostly made out of quads, but not necessarily exclusively made out of quads. So they're not quad meshes that don't have anything else but quads. But they're quad-dominant meshes. That means they can have triangles, they can have larger polygons, but most of their faces are going to be quads. And they're preferred because they perform a lot better when it comes to operations like Cutler-Clark subdivision than other types of polygons. So they're very good. They're very good structures for modeling anything. But once we're done with modeling, once we finished our model and said, okay, this is my object model, whatever it is that I'm trying to model. From that point on, regardless of what type of representation I use for it, I could be using some polygonal mesh for modeling it, I could be using maybe NURB surfaces, I could be using anything else. At the end of the day, once I'm done with preparing my model, I typically convert my model to a triangular mesh. And there's a very good reason for that. And here it is. Triangles are nice. A triangle can be defined by 3 vertices in space, just 3 points in space. And I can just move them around however I like so. And these 3 vertices in space, 3 points in space, will define a unique plane. Just one unique plane. And this is going to form a planar, that means a linear shape for me. The same cannot be said for higher degree polygons. So if I have a quad, the 4th vertex here, that would form a quad, it doesn't have to be on the same plane as these 3 vertices, right? And if it's not on the same plane, the shape that this quad will represent is not going to be necessarily a rectangle or some planar. It's not going to be a planar quad. It's going to be a deformed. It might be a deformed quad. Actually, what it represents more specifically is going to be a bilinear patch. A bilinear patch is a funny shape. It's formed of linear lines that connect the edges, but its shape is actually curved. It's a relatively more complicated shape than a triangle or a planar surface. But we don't want to deal with the complexity of that. Instead, we're working with simpler shapes that are planar shapes and triangles. And there are good reasons for that, and I'm hoping that at the end of this lecture, this is going to become clear why we would prefer triangles. But if you want to have curved surfaces, if you want to have more detailed curved surfaces, what we typically do is that we just use more and smaller triangles, right? Just you add more and smaller triangles and you will have a representation of a curved surface. So we use triangles as our building blocks. So we just connect these vertices in space and we get a triangle, right? Triangles are nice. So as I said, if I want to have a sphere, I can just do something like this, right? I can put a bunch of triangles together. I have a triangular mesh that represents a sphere. Of course, remember the implicit sphere I talked about last time with the implicit formulation for a sphere. A triangle mesh is not going to be a perfect sphere, right? It's going to be sort of faceted. It's because every triangle here is planar, but on an actual sphere, there are no planar pieces, planar surface pieces. Like the surface of a sphere is always curved. So this is not going to be a perfect sphere ever. But if these triangles become smaller and smaller on the surface, especially when they become smaller than a pixel, then do I care if it's planar at a triangular level? I probably don't, because I can't even see them anymore, right, if they're smaller than a pixel. This relatively simpler building blocks of triangles are very, very useful for representing all sorts of surfaces, all sorts of objects for us. Well, here's our friend. Remember this guy? I love this model. This is all made out of a bunch of triangles, right? It's really nothing else, as scary as it looks. It's made out of a bunch of triangles, and of course they're sort of painted over. It gives you the illusion of a lot of surface detail here, but it's a relatively few number of triangles here. I actually don't know the number of triangles for this particular model. But we know that it's made out of triangles and with some painting over the triangle, the textures. That's going to be our next topic, but I'm not really planning to talk about textures today. Anyhow, you look at this, it's just a collection of triangles. And we use triangles and triangular meshes for representing pretty much any object in computer graphics. I'm saying pretty much any object. By that, I do not mean every object. There are exceptions to this. There are certain types of objects where triangular meshes may not be a perfect representation. A good example of that, and not the only example, but a good example of that is hair. For example, this wonderful model created by Luc Begin, he's a wonderful artist. If you look at this model, most of it is actually modeled as a polygonal mesh and then converted into a triangular mesh and rendered. But not all of it. The hair, not just the hair on top of the character's head, but also the facial hair. And also there's some little particles on the character's shirt. All of those are represented using splines, represented as curves, not as triangular meshes. But most of the surface is actually modeled as a triangular mesh, right? So that's the point. So here's another example. Here again, most of this character model is crafted and built, modeled using polygonal meshes and converted to triangular meshes and rendered as triangular meshes. But not the hair. Hair is modeled differently. I'm not going to get into the details of how this particular hair was modeled. And these splines are what is used for rendering the hair in this example, right? Nonetheless, most objects, if not all objects, or most objects we use in computer graphics are rendered as a bunch of triangles. Even if they're not modeled as a bunch of triangles, they're converted to a triangular mesh before they're rendered. So that's why triangular meshes are very, very important. And I gave hair as an example of an object that is not necessarily converted to a triangular mesh for rendering. But there are methods that actually convert splines to triangular meshes while rendering. So even splines can be rendered as triangular meshes because GPUs are designed to render triangles. So I'll talk about rendering on the GPU in a little bit. Nonetheless, triangles are very important because whatever we do with surfaces, with any kind of objects we have in computer graphics, they may end up being a bunch of triangles in the end, right? So let's go back and take a look at our triangles and try to understand them a little better. Now, okay, defining a triangle is easy. I just have 3 points in space and I define a triangle. Okay, but I defined a triangle, but I kind of need to figure out all the points on this triangle somehow, right? Let's pick a point here, like this point in the middle, this green spot. Let's call it P. Where is that P in space? Just I know where these 3 vertices are. Let's call them P0, P1, P2. I know where these 3 vertices are. But I kind of need to figure out a way to compute the position in space for any point on this triangle, right? That's what I need to be able to do. Turns out that that's fairly easy because this is a planar, this is a planar surface. a triangle as a planar surface, and these 3 points in space uniquely define that plane, any point on that plane, any point on this plane represented by these 3 points can be represented as a linear combination of these 3 points in space. Again, any point on this plane, can be represented as a linear combination of these 3 vertex positions. So I can write this point P as a linear combination. Let's say P is equal to alpha P0, beta P1 plus gamma P2. Good? Just some numbers, whatever they are. Turns out we have a very specific name for this kind of representation. We call it the barycentric coordinates of this position P on this triangle. So this alpha, beta, gamma is going to represent the barycentric coordinates of this point P on this triangle. It's very specific to this triangle, right? Because these are the weights that I'm going to be using to form a linear combination of these vertex positions. And here's an interesting thing about the barycentric coordinates. This is a very, very general concept and used a lot in computer graphics because triangles show up in a lot of places. One interesting thing about this is that these barycentric coordinates will have 3 components, right? Because it's defining a position on this triangle, let's say. But I'm not saying anything about the dimensionality of these vectors P0, P1, P2. So this could be a 2D triangle. Right? It could be a 2D triangle such that P0, P1, P2 only have X and Y coordinates. I would still have 3 coordinates here to represent my barycentric coordinates, right? Because it's just the weights of these 3 vertices. Or this could be a, 4-dimensional triangle. Can you define 4-dimensional triangle? Very easy. You just pick X, Y, Z, let's say W, for these points to represent their positions in 4 dimensions. And that would form a 4-dimensional triangle, or a triangle in 4 dimensions. And again, it's going to have this 3 coordinates representing its barycentric coordinates for any points on this triangle. Now, these barycentric coordinates, they're supposed to represent a position on a plane, but I have 3 components here. That's a little odd. Now, for some of you, you may think, okay, this is normal. I have 3 vertices. Of course, I have 3 coordinates. But a plane is a 2D construct. So on a 2D construct, I actually don't have 3 degrees of freedom. I should be able to represent positions on a plane using just 2 values. Think about this. A position on a line, it's very easy to think about, right? A position on a line, you should be able to represent a position along a line using a single value. Right? It's just if you have a reference point, you call it as 0. Any other point along that line can be represented by how far that point is from this origin point that you picked, right? So a position on a line, you can represent it using a single value. A position on a plane, being a 2D construct, I should be able to represent it using just 2 values. I shouldn't need a 3rd one. But I have 3 values here, so that's a little odd, right? When you think about it that way. Actually, it's not odd, because it turns out the barycentric coordinates, because of this, has a very specific property. That is, these coordinates must always add up to 1. So these are not completely independent values. They are actually dependent to each other. And they need to add up to 1. Right? So if I know 2 of them, alpha and beta here, I can compute the 3rd one. Right? Because they must always add up to 1. And this sort of makes sense because at the end of the day, what I'm trying to do here is just a linear interpolation of 3 values. Right? So it's just the average of 3 values. So they must add to 1. right? So we talked about this while we were forming curves. Whenever you're averaging things, they must add up to 1. If they don't add up to 1, you're sort of secretly adding a zero vertex here somewhere, right? That has the remaining weight. So whenever you're doing an average of 3 values, they must add up to 1. And that's the only way I will guarantee that this point P is going to be on the same plane defined by these 3 vertices in space. Right? That's the only way that I can guarantee it. This equation must be satisfied. So this is a very, very important equation. Barycentric coordinates will always satisfy this equation. All right, good. Now, I said that this point P on this triangle can be represented as a linear combination of these 3 points using barycentric coordinates like this. But this is not specific to the points on this triangle. I can actually represent any point on this plane as a combination of these 3 vertices. Literally any point on this infinite plane can be represented, such as this one that's outside of the triangle. Any point on this plane can be represented like so, as a linear combination of these 3 points. Again, the barycentric coordinates will add up to 1, right? But if this point P is on that triangle, then I have an additional nice property that these barycentric coordinates will always be positive and smaller than 1. They will always be positive and smaller than 1. Now, this property that they all add up to 1, that always exists. And if they are all also between 0 and 1, then this point P is going to be inside that triangle, right? And if point P is outside of the triangle, then this property that alpha, beta, gamma being positive or non-negative and smaller than 1, it doesn't hold anymore. So it's gone. So if the point is outside of the triangle, then that property is gone. But if the point is inside the triangle, then I have this property. It's a very, very useful property. So just to give you some intuition about what barycentric coordinates are and why we like it so much in computer graphics. Now think about it this way. If I take this point P, that point P over here, and if I move it to one of the edges, I'm going to move it to the edge between P0 and P1. Right? See, I'm moving it to the edge between P0 and P1. What happened to my third barycentric coordinate is it just went to 0. And that kind of makes sense because now point P is between P0 and P1. So it should be represented as a linear interpolation between P0 and P1, right? It's along the line that crosses P0 and P1, so it doesn't depend on this P2 anymore. So P2's weight is going to be 0. So for a point along one of the edges, one of the barycentric coordinates will have to be 0, right? What if I take that point and move it towards one of the vertices? If I take it and move it towards one of the vertices, then 2 of the weights are going to be 0, and the other one will have to be 1 because, this property always holds, right? And that kind of makes sense. Well, I just took P and put it on P0. So, yeah, the others are 0, and then P0 is 1. I mean, what else can it possibly be? So, as you move this point from one of the vertices towards the opposing edge, its weight is going to go from 1 all the way down to 0. And if you move it even further out of the triangle, then its weight is going to start becoming negative, right? It's not going to be between 0 and 1 anymore, right? So that's the property of our barycentric coordinates, and we can compute this for any point on this triangle, also anywhere on this plane. And we can do this for computing the positions, the exact positions for any point on the triangle, which is very nice. But we don't just use it for computing positions on the triangle. We also use it for computing all sorts of attributes on this triangle. Now, we're working with triangular meshes. Triangles are going to be our discretization of the surface. So, whatever property we define on our surface is oftentimes going to be stored at these vertices, right? I'm going to be storing some attributes at these vertices. And to find the value of that attribute at any point on the triangle, I can do the same thing. I can again use barycentric coordinates to interpolate the value of that attribute. For example, instead of positions here, I can just assign some colors to these vertices. Let's say that I'm assigning the P0 is going to be red, P1 is going to be green, and P2 is going to be blue, right? Let's do it. I did that. All right, so the triangle is just interpolating these color values, right? And to find the color value at any point on this triangle, I can just do this linear interpolation using my barycentric coordinates. So barycentric coordinates are very frequently used for rendering, and they're very nice and very simple, and that's probably one of the reasons why we like triangles so much, because they're planar and they form linear interpolations, and those linear interpolations can be represented using barycentric coordinates like this. It just simplifies the whole rendering process quite a bit, and that's one of the reasons we like them so much and we use them so often. All right, and this is not specific to position or color. Like any attribute you can think of that you can add to a vertex. If you want to find the value of that attribute any point on the surface, you would just look at the corresponding triangle and find the barycentric coordinates of that point and do the interpolation. What did I say? I said something scary. Did you catch that? I said actually something scary. I said compute the barycentric coordinates of a point. Let's see how we can do that. Now I kept saying, if you give me alpha, beta, gamma, or like if you give me the barycentric coordinates, I can tell you where that point is. That's very easy, right? What if I want to do the exact opposite? What if I give you a point on that triangle and I say, well, give me the barycentric coordinates? Like, why would I ever need that? Well, let's say that I know the position on the triangle somehow, but I want to be able to compute the values of these other attributes that are stored on these vertices, right? And to be able to interpolate those attribute values, I need to know the barycentric coordinates of this point. So how do I do that? Well, there are various ways of computing the barycentric coordinates. I'm just going to show you one of them that I find to be sort of intuitive and nice. Now, what I'm going to do is I'm going to take this point in the middle here, and I'm going to use that point to split this triangle into 3 triangles, like so, right? I split my triangle into 3 triangles. Okay? And here's what I'm going to do now. I'm going to compute the area of these smaller triangles here. The areas of these smaller triangles. And I'm going to label them like so. This was my vertex 0, right? P0. So the triangle that is opposing to that vertex, I'm going to label its area as A0. Okay, so this one was P0. And the opposing triangle on the other side, I'm going to call its area A0. I'm going to do the same for the others. So A1 is going to be the area of this triangle, and A2 is going to be the area of the remaining triangle. Now, if the total area of this triangle is, let's say, A, then my barycentric coordinates can be written as these. A0 over A is going to be the barycentric coordinate of P0. That's going to be alpha. And A1 over A is going to be the barycentric coordinate of this point. And A2 over A is going to be the barycentric coordinate for this vertex. And why is that? Well, let's see if this makes sense at all, right? So I know that my barycentric coordinates, they're supposed to add up to 1. Do they add up to 1? Well, I know that the total area of the triangle is A, so A0 plus A1 plus A2 is equal to A, so these weights will add up to 1. Okay, at least we're okay with that. That part seems to check out. All right, let's take a look at the other properties. Now imagine that this green point is along this line over here. If it's along this line, what's going to happen? If it's along this line, that means my alpha barycentric coordinate will have to be 0, right? Because the point is just going to be a linear interpolation between P1 and P2, right? And again, if this point is along this line, look at the area of this triangle over here. The area of that triangle is going to be 0, right? That triangle is going to collapse. So, okay, so when alpha is supposed to be 0, A0 is 0, that kind of makes sense. That's great. What if I take that point, that green point, and move it all the way on top of this P0? If I move it all the way on top of that P0, then the area of A0 will be equal to A, right? It's going to cover the entire triangle. And so the alpha value will become 1 and the others will be 0. The other two triangles will collapse. So intuitively, seems like it is working. And yeah, so this relationship exists. There are other interesting relationships as well with the angles of these triangles. You can also compute the barycentric coordinates, but yeah, I'm not going to get into that. It's just one way of computing the barycentric coordinates. All right. So are we going to do this? Maybe, but just not yet. So this is going to be something that our GPU is going to do for us while we're rendering. That's very nice, right? So you won't have to worry about this too much. But it's good to know that this is happening. So, remember this guy? This GPU rendering pipeline? I call it GPU pipeline. So we feed in triangles on one end. Those triangles come to our vertex shader as a single vertex at a time. In our vertex shader, we transform them into the canonical view space. And then our rasterizer gets those vertices in the canonical view space and their primitives, their triangles, and it rasterizes them, excuse me, and forms these fragments, and those fragments are sent to our fragment shader, and the fragment shader computes the color, and we get our image. So this is our regular rendering pipeline. Now let's take a look at over here. What's happening here is that our rasterizer is producing these fragments that correspond to the pixels. Now, its input is going to be the vertex positions in canonical view space, these 3 vertex positions and the other one, and along with whatever attributes we store at these vertices. So our rasterizer, okay, technically our rasterizer is not directly going to get, but nonetheless, our rasterizer is going to get the canonical view space positions for these 3 vertices. And it's going to compute the canonical view space positions for all of these fragments. And it's going to compute, more importantly, the barycentric coordinates for these fragments. Well, how do I compute a barycentric coordinate for a square? I don't do that, right? So when we think about a pixel, remember we talked about this, pixels are not little squares? We talked about this, right? So think about a pixel as like a sample of an image. So what GPU will actually do is it will look at the centers of these pixels, like center points of these pixels. And the GPU will compute the barycentric coordinates for the centers of these pixels for these fragments, right? And if I know the barycentric coordinates of these points that correspond to the centers of these fragments, then I can use those barycentric coordinates for interpolating any of my vertex attributes. So our GPU is going to do that right before calling our fragment shader here. Right before calling our fragment shader, our GPU is going to do that interpolation. So if you remember, our fragment shader and vertex shader and fragment shader would look like this. So here I have a varying vector 4 that's color. I'm specifying a vertex color in my vertex shader. That is a vertex attribute. And that's going to pass through my rasterizer here. And after the rasterizer, I will know the barycentric coordinate. My GPU will know the barycentric coordinates. And using those barycentric coordinates, my GPU will automatically interpolate those values and give me the value that corresponds to the center of the fragment. Right? So the value that I get, the value that I receive in my fragment shader, is going to be that interpolated attribute value. Right? And my GPU doesn't know what I'm going to do with that attribute. Like I'm writing the code here, I could do whatever I want with it. It just knows that it's some value, some varying value, so it's going to interpolate it and give it to me, my fragment shader, and I'll do whatever I want with it, right? So this is not, what I'm trying to say is that it's not specific to computing colors. You could use it for computing pretty much any kind of attributes. But color is a good example, good simple example. That's why I keep using it here in these slides. So let's take a look at how to structure all this stuff in WebGL a little bit. But let's go back to triangular meshes. So remember we talked about how to store polygonal meshes, and we had a list of vertices for polygonal meshes and a list of faces, list of polygons. For a triangular mesh, that's going to be a list of triangles. So our faces are triangles, and each triangle will have 3 vertex indices. Obviously, right? So this is a very typical way of representing triangular meshes. Although we don't necessarily send our GPU this structure. Remember we also talked about edges, maybe storing edges in different formats. We're definitely not going to do that for GPU rendering. We won't need the edges. For GPU rendering, we will not need the edges. For some specific algorithms that use GPU-based rendering, they may use edges, but GPU will know nothing about edges. Edges don't exist for GPUs. Right? GPUs will know vertices. GPUs will know faces. They will call them elements. That's about it. Right? And these vertices, they don't have to be vertex positions. The vertices will contain all sorts of vertex attributes, not just positions, but they could be all sorts of other things as well. So. But a typical vertex attribute, of course, is going to be positions, right? So in most cases, my vertex positions will be stored. Now, I've shown you something like this earlier. So it's just XYZ, 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 XYZ positions for my vertices. But this is typically, you should think about this as like a 1D array of XYZ values. So XYZ, like scanline order, X, Y, Z, and then go back X, Y, Z, and X, Y, Z. So this kind of looks like a 2D array, n by 3, that's what it looks like. But it's not a 2D array, it's actually a 1D array, X, Y, Z, and then the next X comes, and then the next X, Y, Z, and then the next X comes, X, Y, Z comes, and so forth. Does that make sense? It's just like the RGB image, or RGBA image. I can do the same thing for my color values. If I have vertex attributes as colors, I can have another list like this. Actually, just to be complete here, there are ways to combine these lists together, and you can even store your vertex attributes as position and then color of one vertex, and then go to next vertex position color and then next vertex position color. You can do all sorts of crazy things. It's very customizable the way that you send data to the GPU. But just to keep things simple, for the time being at least, let's assume that these are separate arrays. And it's okay. You know what? I'm actually going to just get rid of these colors. Colors are gone. We're just looking at positions, right? I have positions, but I could have other attributes as well. But I'm just looking at positions. Now, when I want to render a bunch of triangles using my GPU, we did that earlier when we were talking about WebGL. So I'm sort of repeating myself here a little bit. The first three triangles here, they are going to form the first three vertices here will form the first triangle, all right? And the next three vertices will form the next triangle. And if I want to draw this, I can just use this lovely WebGL command, GL draw arrays. So presumably I put these arrays on GPU memory. Now I'm ready to draw. Of course, I need to do some initialization. We talked about all that stuff earlier, so I'm skipping those steps. So by calling this GL draw arrays and saying that, hey, I'm drawing triangles, and I'm going to draw vertices starting from vertex 0, and I'm going to draw 6 vertices. Because it's 6 vertices and I'm drawing triangles, that means I'm drawing 2 triangles, right? And my GPU will just draw 2 triangles using this. Good enough? All right, well, good enough, maybe not. Now here's the problem. Now if these 2 triangles are the triangles of a quad, in this case actually, let's say that they are, and let's say that these blue vertices are actually the same vertex, and these red vertices are actually the same vertex. The problem with this representation is that, you know what, let me color these position values based on which vertex they represent. So as you can see, this red vertex appears twice. It appears here and it appears down here. And the same goes for the blue vertex. It appears twice, right? And that's not very good. I keep repeating the same data and I'm storing the same data on GPU memory. Actually, with this kind of representation for a triangular mesh, on average, you would expect a vertex to appear, let me see, 1, 2, 3, 4, 5, 6 times. 6 times. Yes, every vertex 6 times. That means this array will have 6 times more data than it needs to have, which is not very good, right? Yeah, especially if you're rendering very high resolution models. That's going to be a lot of unnecessary vertices that maybe I don't have to store. What I actually have here is I actually have just 4 vertices. I actually just have these 4 unique vertices. That's it. I don't have all those 6 ones, right? Even for a simple case like this, I ended up adding more vertices. And for a general mesh, you would expect a vertex to be duplicated 6 times on average. So can I get around it? Well, I can. I can just define my triangles. OpenGL and WebGL will call them elements. So I can have an array of elements. An elements array will contain indices into this triangle array. So that's going to be 0, 0, 1, 2 will be the indices of these vertices. Vertex 0, 1, 2 will be the first element, that is the first triangle. And then it says 0, 2, 3 will be the next triangle. So the first triangle is going to be formed by this 0, 1, 2, and the next triangle will be formed by 0, 2, and 3. And this way I have my 2 triangles. Now, here also, I am going to be duplicating vertices. These same vertices will again appear 6 times on average because a vertex will be used by 6 different triangles. But every time I'm repeating a vertex here, I'm only storing one index. And that one index can be just one integer instead of 3 positions plus all sorts of vertex attributes, whatever attributes I have, right? I'm not duplicating all of vertex data, I'm just duplicating its index, which is a lot cheaper than duplicating the entire vertex, right? So, this is, in many ways, it's preferable. Okay, simple enough, right? Well, alright, drawing this is going to be a little more difficult because now I need to tell WebGL here to use this elements array for drawing. So if I were to draw this and I say just draw me 2 triangles starting from 0, this is not going to work because this buffer is not set up to draw like this anymore. It's not duplicating any vertices. So yeah, this is not going to work. What I'm going to have to do is I'm going to have to use a different command for drawing these elements, and that's going to be the command that says gl draw elements. In gl draw elements, I'm saying I am drawing triangles starting from the very first element, and I'm going to be drawing 2 elements. Each one of them will have 3 indices because they are triangles. So this way I got rid of I didn't get rid of duplication, but I minimized the duplication quite a bit because I'm only storing an index instead of storing all of that data. This buffer is going to be a special type of buffer. It's going to be an element buffer. So you're going to have to allocate an element buffer and then put in some integer values. Those integer values don't have to be 32-bit integers. They can be 16 bits. They can be 8 bits. If you just have 256 vertices, then you could just use 8-bit values. They're going to be even smaller. Setting this up is actually a little bit easier because its meaning is more clear. There's less customization going on for the elements area. I mean, what else can it possibly represent? It's just vertex indices of triangles. Right? So it's fairly easy to set this up. And then you need to call gl draw elements if you want to use elements for drawing. So this is just another way of drawing, and this is more efficient. So one element in this case will mean exactly 1 triangle, yes, because I'm saying my elements are triangles. But I could be using this sort of rendering for drawing line segments as well. In this case, I would be calling GL lines, right? So it didn't have to be GL triangles. But because I called it triangles, my elements in this case are triangles. Alright, so I'm rendering triangles like this. This seems to be more efficient. But there are better things I can do. This is not the best. I can do better. Now remember this array. These are my vertices, right? So if I put my vertices in a specific order, if I carefully order my vertices around, in this case, what I'm going to do is I'm going to take the first vertex and the second vertex, and I'm going to swap them. I'm going to shift their places. If I swap them, instead of starting with red, I'm going to start with green and then red, right? Green, red. So if I do it this way, then here's what I can do. I can render this buffer in a special way, and it will render as it will just draw the first vertex, and then the second vertex, and then the third vertex. Well, I have 3 vertices now. 3 vertices will define a triangle, so I can form a triangle. Alright? Then I'm drawing my 4th vertex. Now I look at the last 3 vertices I drew, and those 3 vertices will define the next triangle. So this is what we call a triangle strip. So if you order your vertices carefully, you might be able to draw your mesh using triangle strips. So in this case, I can draw it using triangle strips just like this. I'm saying I'm not drawing triangles now, I'm drawing triangle strips. So every group of 3 consecutive vertices will form a triangle in a triangle strip. And I'm saying I'm starting from 0, and I'm saying I'm going to draw 4 vertices. That means I'm drawing 2 triangles in triangle strip format. Right? So a triangle strip, just let me give you a longer example of a triangle strip. Let's say this was my first vertex. I have another second vertex. I can't do anything with 2 vertices just yet. I add a third vertex, and as soon as I have 3 vertices, now I can draw a triangle. Now I add another vertex. With the last 2 vertices, it forms another triangle. And I add another vertex. With the last 2, it forms another triangle. Add another vertex, that becomes another triangle. Another vertex, another triangle. Right? Another vertex, another triangle. And you get the idea. So moving on the surface like this, if I carefully order my vertices, I might be able to take advantage of this and store less data for my vertex attributes in my vertex buffers, and also draw my object more efficiently, because these vertices will be transformed. They will pass through my vertex shader only once, right? And I'm sort of reusing the same data that comes out of my vertex shader to draw 2 triangles. All right, so this is actually, each vertex here is used for drawing 3 triangles, so it's actually fairly efficient. So the problem with this is now I need to take my polygonal mesh. I mean, I can convert my polygonal mesh to a triangular mesh. That's relatively simple. But beyond that, I also need to figure out these triangle strips out of that as well. I kind of need to order my vertices, and it's a little bit of a mess. Yeah, that's going to be the difficulty here. For example, if I wanted to draw a model like this, I'm going to have to draw it in multiple triangle strips. Or maybe, in some cases, I might figure out a way to generate 1 triangle strip that goes around the entire model and draws it as just 1 giant triangle strip. But a lot of times, I may need to actually separate it in multiple triangle strips like this. And I like this sort of visualization a bit, because it's showing that, you know, like as I'm moving along a triangle strip, things are very efficient, right? But a triangle strip is just a strip, and on either side of that strip, I have vertices, and I'm going to be duplicating those vertices when I'm drawing the next strip above it, or the strip right below it. So imagine this brown strip over here. This green strip is sharing some of its vertices along their border, right? So those vertices will be duplicated in my vertex buffer. Yeah, and they're going to be processed multiple times. So, I mean, that part is not ideal. But the rest of it is, you know, at least I'm not duplicating each and every one of them. But in this case, my duplication is a lot less. I'm duplicating them only 2 times instead of 6 times, right? So each vertex, on average, will be duplicated 2 times, just so that I will be able to draw them. But we can do one more thing. We said we can draw triangles, we can draw triangle strips. The other form of using sort of strip-like construction is a triangle fan. Triangle fan is sort of like a funny thing. It just forms a fan, as you would imagine. So it's going to use the first vertex. Let's say this guy is the first vertex here. All triangles will be using the first vertex and the last 2 vertices. So instead of a strip that just starts from somewhere and moves on, a triangle fan is going to always use the very first vertex, and it's going to form a fan around that vertex. That's why it's called triangle fan, right? Triangle fan is not that frequently used. Triangle strips are very, very frequently used, actually. But with GLDraw arrays, you can do any one of these 3 when you're drawing triangles. You can draw triangles separately, or you can draw them as triangle strips, or you can draw them as a triangle fan. whichever one you like. But we're not done. Remember, we sort of minimized our duplication cost with triangles when we use an elements array. We can use an elements array with these two. There's nothing stopping us. The same thing will apply. It's just that this time our elements array will be forming strips or fans. So I can just call GeoDraw elements using triangles or triangle strips or a triangle fan, in which case my index duplication is going to be minimized by this formulation. Also, it's going to be more efficient for the GPU to process them. It's going to have to process less data that way. So the most efficient one of all of these for general purpose problems is going to be using elements as triangle strips. So this is going to minimize the data duplication, minimize the cost of data duplication, and it's going to have the efficiency of drawing triangle strips. So this is probably the best option out of all of these, using elements with triangle strips. But what I'm going to ask you to do in our upcoming project, for which we're going to be drawing triangular meshes, I'm going to be asking you to do this. Just draw triangles, because this is the simplest option here. Yeah, we're duplicating everything. We have 6 times the cost of storing data and 6 times the cost of processing all the vertices too. But don't worry about it too much. It's Vertex processing is relatively fast, so even if you're rendering a relatively high resolution model, you probably won't see too much of a difference. Unless you're rendering millions and millions of vertices, it's hard to see the cost of Vertex processing with modern GPUs today. So yeah, this is going to have some, it's not going to be the most efficient one of them all, but it is by far the simplest one of them all. You won't have to form strips, which would be, a little bit complicated. You also won't need to worry about generating an element array. Just to keep things simple, I'm going to recommend that you use this one for all of the projects in this class. But I wanted to, I had to mention this because this is a more efficient way of rendering things. And if you look at any production code, you'll probably see more of this than this guy. All right. So this is all I plan to talk about regarding triangular meshes. All right, then. We'll end it here for today. Thank you all for tuning in, and I'll see you next time. Yeah, thank you.